Okay, in this video I'm going to talk about moving charges and how we can predict the motion of them. One of the problems we have with moving charges is that Newton's laws often don't work. So when do they work and when don't they? Well, the problem with moving charges is that the distance between them changes a lot as they move along. So let's say this particle moves from A to B. This radius 1 in comparison to radius 2 isn't similar at all. What that means then is that Coulomb's law, or the electric force acting on this particle, is changing a lot during the motion of this particle. When we are dealing with objects experiencing the force of gravity on the Earth, we're recognizing that the Earth is very large and the amount that they might be changing is very small. So the radius from the center of the Earth to the object is very constant, which means the force of gravity is basically constant. But here, since this r is changing, the force is changing. And for our 5 equations of motion, we assumed constant acceleration. So if we have a changing force, we do not have constant acceleration. And so we can't use these. And so we can't really use our forces approach. Now later, if you continue to study physics or you continue to study things like this, you'll learn how to deal with changing forces. But right now, with what we've learned about Newton's laws, they just won't work. This is true when I'm dealing with point charges, but not totally true when dealing with parallel plates. Recall, the reason we like parallel plates so much is that the electric field in between them is constant. This means the force acting on a charged particle is constant, which gets us constant acceleration, which means our 5 equations of motion are good again. So when we're dealing with point charges, we can't use the 5 equations of motion, but when we're dealing with parallel plates, because of our constant electric field, constant force, and resulting constant acceleration, the 5 equations of motion are good again. So in these electricity calculations or questions, we have to figure out which of these cases we're dealing with to figure out whether or not we're allowed to use the 5 equations of motion. And on top of that, we recognize that if we can't, then the alternative is going to be energy. Energy will work in all of these situations, and so it may be preferable to just use energy anyway, but one way or the other, we got to be careful here. So let's deal with a question with 2 point charges that we can't use Newton's laws for, and we'll see how we can use energy. And then we'll deal with a question, I think the next one here, with a couple of parallel plates, where we could do it either way. So first of all, 2 alpha particles are 1.5 nanometers apart. If one of the particles is allowed to move, how fast will the charge be moving when they're far apart? And of course, we're ignoring gravity because they're individual particles. So recall an alpha particle is basically a helium particle with no electrons, or a charge of 2 plus. And so the charge on the alpha particle is going to be 2 times the elementary charge of 2 times 1.6 times 10 to the negative 19 coulombs, or 3.2 times 10 to the negative 19 coulombs. And that goes for both alpha particles. And then this guy's going to fly away. And the mass of the alpha particle is 4 times the relative atomic mass, or 4 times 1.6 times 10 to the negative 27 kilograms. So I get 6.4 times 10 to the negative 27 kilograms. So when their two are close together, they have electrical potential energy, which I've been using the symbol U for, so I'll stick with that. U. And when they get far apart, we're going to assume that all of that electrical potential energy is being converted into kinetic energy. So here, K, Q, Q over R is the formula I use for point charges and electrical potential energy, and that's being converted into kinetic energy. We're going to assume that this is non-relativistic, or we're going to ignore any sort of relativity things that might happen here. Solving this for velocity, I get that the velocity is equal to the square root of 2 kqq over rm. So let's figure out what that is. 2, 9 exponent 9 times 3.2 exponent negative 19 squared, divided by, how far apart did I say they were? 1.5 nanometers, remembering that nanometers means times 10 to the negative 9, divided by 1.5 exponent negative 9, divided by 6.4 exponent negative 27. And so these particles would have a velocity of 1.4 times 10 to the 4 times 10 to the 4 meters per second. Electrical potential energy converted into kinetic energy. I can't use my forces because, again, the changing radius means the force acting on these particles changes too quickly, and so I can't assume that I have any constant acceleration. Alright, here's our example with a set of parallel plates, and we're going to see how with parallel plates we really can use energy or forces to solve the problem. A proton is allowed to accelerate from a positive plate to a negative plate in a set of parallel plates with a voltage of 120 volts. Determine the speed of the proton when it reaches the negative plate. So the proton will have the elementary charge of 1.6 times 10 to the negative 19 coulombs. And if I'm going to do this from an energy perspective, I'm going to go that my potential energy that it has from being at one plate is going to be converted into kinetic energy. And for a set of parallel plates, for the potential energy, I'm going to use the fact that I can say that potential energy is equal to the voltage times the charge. And here I'm going to have 1/2 mv squared. So 120 volts times my charge of 1.6 times 10 to the negative 19 coulombs of energy is getting converted into 1/2. The mass of a proton is 1 times the relative atomic mass, so 1.66 times 10 to the negative 27 kilograms. Times the speed squared. So I get 1.92 times 10 to the negative 17 joules of energy. Here I got 8.3 times 10 to the negative 28 kilograms. If I divide that by 2, v squared. Dividing both sides by 8.3 times 10 to the negative 28 kilograms. And cancel both of them out and square root. So the velocity of my proton at that other plate is 1.52 times 10 to the 5 meters per second. So that's using energy. I can use forces as well. going to have to go a little quick here. I'm running out of time. So my electric field here is going to be equal to my voltage over the distance between my plates. I don't know the distance between my plates, so I'm just going to leave it in as D and hope that it will go away eventually. So my electric force is going to be equal to EQ, which is going to be equal to 120 volts divided by D times 1.6 times 10 to the negative 19 coulombs. And so I'm going to get 120 times 1.6, negative 19, 1.92 times 10 to the negative 17 Newton meters. Okay? Now, per distance. So that's my force. So my acceleration would be force over mass. Should be 1.92 times 10 to the negative 17 Newton meters divided by my distance, all divided by my mass. My mass for one proton is still 1.66 times 10 to the negative 27 kilograms. So I have an acceleration of 1.16 times 10 to the 10 meters per second squared divided by D, and actually that divided by D means that meters would actually be meters squared per second squared. Okay, assuming I'm starting from rest, I'm traveling a distance D, I'm interested in V2, and I have my acceleration. So the equation I'm going to use here is 2AD equals V2 squared minus V1 squared. So 2 times 1.16 times 10 to the 10 divided by D times D equals V2 squared minus 0. And look, our D's cancel out nicely. So I take this number times 2, square root it, and I get V2 is equal to 1.52 times 10 to the 5 meters per second. So maybe a little bit more confusing to use forces because I have to leave the variable D hanging around throughout the problem. If I had been given the distance between the plates up here, it would have been a little easier. But in the end, whether I use an energy approach or a forces approach, because the electric field between the two plates are equal, or equal is constant, both approaches work just fine in terms of predicting that final velocity.